Okay, cool. So how many of you were able to run the script that we did yesterday? How many of you got the graph in the same manner that I had got it? Two, three. Who else? Others didn't do the coding part or what? Mhm. What about Srishti, Sri Lakshmi, Ananya? Yes. Okay. Cool. So I told that there was a catch in the code, right? How many of you were able to get it? Can you please tell me what the catch was? Put it in the comments if you can't unmute yourselves. No issues. I can either tell me directly or you can mention it in the chats. I mentioned in the WhatsApp message, right? Please make it fast because we have a lot more to cover today. Some really important concepts. So in the last, after the last class, I sent a WhatsApp message that you should do the coding part. If you haven't completed it, you should do that because I left a small catch in there. You were supposed to find out. None of you actually found it out. If anyone has got it, just mention it in the chat. No one? Okay, let's not waste time on this. Let me get back to the same code that we did. Right, it is the same code that I typed yesterday. Now this was the output we got. Correct. Now, if you look at the R square metric here in this example, it is minus 1.25. And earlier when I was explaining the theoretical concept, I told you that the R square metric is supposed to vary from 0 to 1, right? Where 1 making the model perfect and 0 making the model like it is doing nothing, useless, right? What is this minus 1.25? I was expecting somebody to point out in the last class itself, but nobody did. So I thought, okay, maybe I'll keep it this way. I'll let everyone execute the code after watching the video or something, then come back with the same question in the next day. But apparently nobody did. Now, why is it coming as minus 1.25? We know that 0 means the model is not doing anything, right? However, what does minus 1.25 mean? Just give me a second. Yeah, sorry about that. Right. Now, let's look at it from a different perspective. Okay. Say, look at the matrix here. Y mean is 7, variance is equal to 0.0. Now, if you look at the R square formula, it is nothing but 1 minus MSC divided by variance, right? Now, let us just assume that in this MSC place, if I put in the variance itself, what is variance? Exactly, it is yi minus y mean, right? Yi minus y mean. That is the formula for variance, 1 divided by n summation of yi minus y mean squared, correct? So if instead of the predicted value, if I simply put in mean itself, sorry, variance itself, that means what? In the place of y predicted, I am putting in y mean. If I'm simply predicting the mean value instead of any modifications, right? The average value. So in this case, it is going to be somewhere around 7, I guess. Yeah, mean is 7, right? Yeah, mean is 7. So if my model simply predicts 7, then the R square metric becomes 0, correct? That means what? We are getting minus 1.25 means what? Our model is behaving or performing in such a bad way, or our model is so bad that it can't even keep up with the performance of predicting mean value. It is that bad we have created this model. Okay, if I simply draw the this one, what is it? The mean line, right? Let me just put it a small line here. PLT dot AX line, AX horizontal line, right? Then what is it? Y underscore mean. Let's give it some color. Color is equal to maybe green is good. Anything is fine. Line is fine. Let's make this also minus minus dotted line, dashed line. Input is equal to, let's make it 2. Let's label this. What is this label? It's the mean. Okay, just run this code. If you look at this horizontal line, right? This is the mean value that we have. 7 exact to be precise. Now, if you look at the placement of these data points, correct, comparatively, it is better with respect to the predicted line, the blue line, right? So if I have to calculate that exactly, I will have to make the W to be 0 because I am not even caring for X. And then B, we need to make it as 7. Why? It is the mean value. So if I run this, like this, right? This is my predicted line, which is nothing but the mean value. The errors are comparatively smaller and R square metric came to be 0. Means what? My model is explaining nothing. This is the baseline performance that we can expect. Like even if it is a pathetic model or the line that we have put is simply doing nothing, at least then R square metric is coming to be 0. But when we made it 3 and 2, right? The line is so bad that it is actually not even underperforming, it is performing in the negative implication. Makes sense? Yes, right? Okay. Now the question comes, how do you tune the W and B values so that we do not come across these kind of situations, right? So for that, let's move on to the next concepts. Let me stop sharing this window. I will share my board. Yeah. Then, so the idea here, right? We tried to guess the values of W and B in the last class, and for some specific value, we even got the R square to be 1, which was a really good performance, right? It was simply sitting with the actual data points. However, that is not going to happen if we are working with a complicated data, right? Here we were able to find them out using some iterative method just by wild guessing. We were able to fit the line perfectly. But what if it is not possible? Because that is the big question, isn't it? Even I think Ananya asked yesterday how to decide on W and B values in the last class. This is how we generally do. If we want to automate finding the value of W and B, there is an algorithm called the gradient descent. Okay, what is this? Is the purpose of this particular class. So essentially, what is the goal here? To reduce MSE, right? MSE has to be reduced to the maximum extent possible, or we can even say the whole goal of our engine or our optimization is to make it 0, which may not be possible in practical sense, but that is what we are actually trying to do. MSE is supposed to become 0. When that becomes 0, our model becomes what? Perfect. Correct. However, in practical sense, it may not be possible. And yet, let's uh, try to do that. That is what the goal is. Correct. Now, when does this MSE become 0? When y becomes equal to y predicted, right? Correct. Or the y predicted is exactly same as y, only then MSE becomes 0. And then how do you decide what is the value of y cap going to be? Y cap in sense y predicted going to be. It is given by the equation what? Sorry, not A, W, X plus B, isn't it? This is what our model was. Now to reduce the error, we need to fine tune these two values, W and B. Okay. We have a training data set where the X values are fixed. We already have the value of Y to be precise, and Y cap is also something that we can calculate. Correct. Now to optimize this problem and get the best values for W and B, we need to change our perspective where in this example, X is a variable in the general sense, right? W and B are constants and Y cap is the target variable. That is what we are trying to calculate. But when the goal is to tune these two values, we need to treat W and B to be variables and then X as a constant. So here what we do, we already have the set, we keep X as constant value. Okay. And then we treat W and B as variables. We change the values of W and B and calculate Y cap for each combination of W and B, right? And then with respect to this value, we calculate R square, find out whether R square is becoming less or more. Based on that, we again have to change W and B and repeat the process. This is the whole idea. Okay. Now, when do we say that W and B are actually becoming better? When MSE becomes less, right? Correct. When MSE becomes less, R square is going to increase, correct? And that is how we say, okay, we are moving towards a better value for W and B. That is the intuition, that is the implication we can get from this understanding, correct? So let's take this equation. What is MSE is equal to, what is it? 1 divided by n sigma, right? Yi minus yi predicted whole square, correct? What I will do, I will replace this yi cap with the model that I have built. What is it? Is equal to 1 divided by n kept as it is. Then yi is kept as it is minus yi cap is what? Wxi plus b square. Sorry, not plus. Here also it becomes minus because wxi minus b. We are taking the parenthesis minus inside the parenthesis. I hope you understood to till this point. Yes? Yes or no? This is MSc. Yes? You are not able to understand. Okay. So let me go through it once again. Okay. To make our predictions better, we need to reach or make y cap move towards y, right? When these two become equal, then it is the perfect model that we have. Y is actually equal to the predicted value y cap, correct? And how do we do that? When is y equal to y cap? When MSC is 0, correct? Right? Then how to, so that is why I'm taking this MSC equation and trying to find a way if it is possible to make it or bring it to 0 if I can find out a way to do that. Okay. So I have taken this equation, MSC equation here, this one. This we already knew from the fifth session, if I remember it right, right? I had written it in some way like this, and yi minus yi cap whole square whole divided by n. This is how I had written it. It is nothing but this, correct? And in the place of yi cap, I have replaced the actual model. What is yi cap? We have an equation here, right? This is what I have actually replaced here. So if you want the intermediate step as well, it is nothing but 1 over n sigma yi minus wxi plus b, right? Whole square, right? This is what this is. I am taking this minus inside the parentheses, right? And we got this equation. Hope it is clear now. Okay, cool. So now what are the two parameters that we need to change to make y cap closer to y or to reduce MSC? W and B. This is what we understood so far, right? X is fixed. We already have the data. We can't change it. What are the parameters that we can actually change to make it better? W and B. And we consider these two as variables in our next process. Okay. So one thing that I need to find out here is how my W, a change in W is affecting my MSC and how a change in B is affecting my MSC. These two things I need to understand. Okay. So to do that, there is a concept called partial derivatives. How many of you do know about differentiation, or how many of you do not know about differentiation? Let's take that as a vote. How many of you do not know about differentiation? Just raise your hands. If you do, then my explanation becomes easier. If you don't, I will have to go a little deeper. Okay, all these people who have raised their hands don't know about it. Then let's do one thing. Let's take only this context, whatever is needed for us, only that much we will try to calculate. Okay. So say for example, I have a curve, or yeah, I have a curve like this, or yeah, let's take a curve. Okay. A line like this. Okay. Now I take a small piece a segment over this line. Okay. Now I will calculate the value of this line if it is along x and y axis. Okay. Here I will try to calculate the two values. So at some point x, what is the value of the curve? That is going to be this part. Okay. And after a small step that we actually call as delta x or dx. Okay. After a small step, what is the value of the curve? These two we try to calculate. Okay. And it is represented as, if I represent this line as f, then df divided by dx. Okay. With a very small step, we call it infinitesimally small. Okay. The small means the step is like it is very close to zero. That small it is. Okay. Just don't worry if it is not making sense in mathematical way, but try to understand it in the general meaning. We are simply segmenting this line. Okay. In a small interval of delta x or dx. In that small segment, how my line is changing, how the value of y is changing. This is what we are trying to find. And this is what we actually call as a differential. Okay. Generally, this differential gives you the slope of the line at that particular moment. I hope you know, since this dx is extremely small, we can consider it to be a point. I know that the concept is a little confusing. If the line is like this, if my dx is somewhere here, okay, here if I take the derivative, I am essentially calculating a tangent. And what is the slope of this tangent is what this expression tells me. Okay, if you understand this much, that is good enough. So another way of understanding this differential is how a small variation in x is affecting my line. So if I change from x to x plus dx, then how my y is going to change is the interpretation here. Okay, fine. Now, this is the plane differentiation with respect to x. What if the line, is made up of multiple variables in our case here w and b we are taking as two variables. So f of w comma b we need to find out. Df of w comma w comma b, and then yeah, the small change here, that is what we need to find out. Let me don't not complicate it anymore. Okay. To do this, what we generally do is, let me write this particular function. In our case, what is this? MSE. MSE function is this one, right? 1 by n sigma yi minus wxi minus b whole square. This is my MSE function. Now this MSE function is actually we are treating w and b as two variables. So these two are the two variables, right? Now what I do is I will find out how a small change in w is affecting my MSE. And then again, I will try to find out how a small change in b is going to affect my MSE. Okay. To do that, what we generally do is take something called partial derivatives. What does that mean? We It is denoted like this: dou MSE divided by dou W with respect to W, how my MSE is changing. When I use this symbol, it means it is a partial derivative. In that situation, what we do is we simply keep B as a constant value. Okay. And only treat W as a variable. Xi also becomes a constant. Yi also becomes a constant. N also becomes a constant because we are only looking at the changes affected by change in W. Okay. Now, when you do this, right, a partial derivation, differentiation, then there is a rule called chain rule. Just follow this thing. If you don't understand, you will have to go through the video once again. Okay. What does this chain rule say? Say, for example, there is a function f of u where u is another function that is of x. Okay. Then if I try to find out df with respect to change in x. This is u, this is x. Should I take another name? It's okay. I guess you can understand. So in this case, what the rule says is we first find out dfu with respect to du and multiply this with du by, sorry, du by dx. This is the chain rule for differentiation. Now the same concept we need to bring in for this one as well. Because here in this expression, this part, right, this is what we are treating it as u. Because it is what? MSE is equal to 1 by n sigma u square, where u is equal to yi minus wxi minus b. Correct? So what do we generally do? We simply take the differentiation of this first, that is nothing but dfu divided by du, right? Here it is called dou, the partial derivative. And a standard rule in differentiation is if I have say d of x square divided by dx, then the result is, a standard result is 2 into x. Okay, this is a standard rule in differentiation. We are trying to make use of this one. Okay, so now let me write the partial derivative. Dou MSC divided by dou is equal to what? Dou by dou W of over n sigma. What is this? Yi minus Wxi minus b whole square. Correct? So what I am doing? First, I need to take the derivative of this entire term with respect to this formula, this one. So it is going to be what? 1 over n sigma 2 into yi minus wxi minus b, right? And then multiply it with what? The partial derivative with respect to w of this inner equation. With, look at this part, right? So what is it going to be? If there is no term of w here, the change in this term with respect to w is going to be 0 because it doesn't include w at all, right? So this is 0 minus, here we have 1 w to the power 1. So I have 1 into w to the power 0. If you look at this, the power has reduced from 2 to 1, right? So the same concept you can apply here. So w will not be there. Xi is kept as it is, correct? And then minus this one, again this is a constant, and this also becomes 0. So 1 by, I can take this 2 out, right, out of the summation. So it is 2 divided by n sigma. What is this term essentially? It is the error, right? Or I will write it once again. It is nothing but yi minus yi cap into minus xi, right? So this is nothing but error here. We know this, right? Original minus predicted. So this minus sign also I will take outside. Minus 2 divided by n sigma error into xi. This is what? It is the change on MSC with respect to a change in W. Fine. Let me do the same thing for B also. Dou MSC divided by dou B is equal to what? This part remains the same, right? So it is what? 1 by n sigma 2 into yi minus wxi minus b kept as it is, right? Into, now look at the same equation yi, wxi and b. Here we are treating b as the variable and remaining things are constants. So this derivative of a constant is 0. Derivative of another constant is 0. And derivative of b is what? 1. Correct? So we have minus 1. This is essentially nothing but what? Let me write it here. So dou MSC divided by dou B is equal to minus, this 2 is coming out. So 2 by n sigma. This is nothing but error, right? That's it. This one. No need to write. Okay. I hope you have understood some of the concepts. Few things that you should remember. Derivative, sorry, derivative of a constant d by dx of some constant is equal to 0. Okay. And then d by dx of x power n is equal to n into x power n minus 1. Okay. And then the rule called chain rule that I have explained already. These three things, if you know, then it is good enough. I try to explain it as simple as possible. Just go through the video once again if you haven't. Okay. Even then, if you don't understand, you just ask me. I will explain it once again later. Cool. Okay. Please remember this. I will take the same expression later in the program as well. So let us do one thing. Let's call this equation as dw is equal to derivative with respect to w. This is for programming. Okay, is equal to what? Minus 2 divided by n sigma error into xi, and db, the derivative with respect to b, is minus 2 by n sigma error. Okay, these two are important. Fine. Now, now let's look at the same concept from another perspective. So if I plot the error, say for example on x-axis, and this is the y-axis, I'm taking this as the, let's take two things. Let's take one is MAE, mean absolute error, and then let's also plot MSE here. If this is the error value, then +1, +2, +3, +4, right? If the error is negative, means what? Y predicted is larger than the Y actual. In that situation, we get negative errors, right? So -3, -4, right? What is MAE? It is the absolute of error, correct? I hope you remember. So whatever error we have, 1, 2, 3, 4, 5, 6, 7. Let's mark some 2, 3 points, right? Absolute of error. So for -1 error also, it is going to be +1. For +1 also, it is going to be +1. And then for 2, it is like this, right? For 3, right? So if I plot this line, these points, it is going to look something like this, correct? Look at this point. It is a V-shaped curve. At this point is the problem. Okay. Let's also do the plotting of MSE. What is this? It is actually error square, right? So +1, -1, it is going to be the same. Okay. And +2, it becomes what? 1, 2, 3, 4. For +2, it comes to this point, right? And for +3, it goes somewhere around this point, and for -3 also. So the curve, since there is a square, it's going to be a, sorry, to meet here, a parabola, something like this, right? This is the 0 point. This is what MSE looks like. And what does MAE look like? Something like this. Okay. There is a mathematical constraint that you cannot find out the slope of a point, this V point. Okay. However, it is possible to calculate the slope at this point because it is a smooth curve. Okay. Now, the concept of entire gradient descent is that when we assume some arbitrary values for W and P, we may end up getting some MSE, some MSE, we don't know. Okay. It may be somewhere here or maybe somewhere here. Okay, we don't know. Or maybe we are somewhere here, right? Based on the MSE value that we can point out the location. Now from here, we need to change the values of W and B so that we come down towards this 0. This is our goal. Okay. Wherever we are actually doing what? We are trying to descend to 0 point, the valley point. Okay. And the slope of any point here, right? That is what we call as gradient. It's nothing but slope. Okay. And that is the name gradient descent. And in the last class or in the previous class, I told you that there is a reason why we take MSE for this, right? Where is it? Yeah. There is a reason why we take MSE instead of MAE. Why? Exactly for this reason. Square. Okay. just so that it becomes easier for us to do this partial derivative mathematics to arrive at a W value, W and B value. Makes sense? At least some idea you got? Now let me give you one more concept here. Now that I was thinking about it. If you look at this, okay, or let me draw a curve, a separate curve. Okay, let's take this point and this point. Okay, and also this point, right? These two are relevant for us because our curve looks like a parabola, right? So when you are here and moving in this direction, right? How is the tangent going to look like? Something like this. It touches this point, right? In this direction, right? So the slope of this tangent is actually negative. Okay. And when you are moving up at this point, the tangent is something like this, right? And here the slope is positive, right? Now imagine that you are somewhere, maybe there is a hill, you are blindfolded on that particular hill, right? You are somewhere here. Now your goal is to reach the valley point or the foot of the hill, but you are blindfolded, which you don't know which direction to go. How do you assess whether you are going in the right direction or not? When you put your next step, right? If you need to climb it to reach, or when you take the next step, if your feet feels like it is inclined forward, then we say that okay, we are maybe trying to descend, right? When you place the feet in the upward direction, or if you are trying to move in this direction, then your leg feels like what? Something like this, right? Correct? It is inclined in the upward direction, and based on that you will assess whether you are going upward or downward. Correct? The same thing here. The slope is negative. Where is it? Okay, yeah, the slope is negative. You are moving downward towards the point. The slope is upward. You are essentially moving away from the point. Makes sense? If this is the case, somewhere you are around here and the slope is negative, means what? You are moving towards the solution. Correct? So what do we need to do? We need to, since the slope is negative, a general formula gives away the solution. What is it? The updated W is going to be what? Current W, whatever it is, right? Um, Plus the TW. Correct? If it is negative, what is happening? If dW is negative, we are reducing the value of W to get the new W value. Okay. In the same way, updated B is also going to be B plus dB. If it is positive, then we are going to increase the value of W and put it in updated W. This we do this iteratively over number of repetitions. Okay. However, just putting this one as it is makes the problem a little complicated by means of number of iterations. So what we do, we smooth it over by a factor called learning rate. What is learning rate essentially? It is the how it is like how big your step is when you are going up or coming down. Okay. Don't worry, just follow it up as much as possible. We will go to the code and do the same thing. Then you will come to know this properly. Right? I know that you will have to go through the video once again. Understood? Now, for we obviously can understand that just by one iteration, we will not reach here, right? It is something like this. After one iteration, you have reached this point, and another iteration, you reach this point. Another iteration, you reach this point. Then finally, maybe after some iteration, you reach the final value. In the same way, here also, you jump from here to here, W value has changed. Then maybe it is not good enough. You changed again, then again you changed, and then again, like this, you take small steps and come to the optimal point, right? Step by step, you are descending the hill here, either in this direction or in reverse direction. That is why we call gradient descent algorithm. Okay. How big this step is decided by learning rate. Okay. How many steps you are allowed to take or how many repetitions you do, it is called epochs. It's a AI term that is generally used. Whichever model you try to use in AI, you will have to mention this one. number of epochs. Okay. It is simply a fancy term to tell you how many times do I have to repeat. That's it. Understood? So keeping the entire math aside, what are we essentially going to do? We are going to implement these two equations. Okay. We are going to specify number of epochs, then learning rate by ourselves. Okay. We calculate errors in each iteration. Okay. Then to reduce this error, we update W and B for epochs number of iterations. Finally, arrive at some value of W and B, which ideally should have reduced the error to zero, which will not exactly happen, but it will find out the maximum point that is possible. Like the least errors we can get, what is the best fit, it will try. However, the number of epochs, if you increase, it will try to bring the point, the W and B value to the exact solution. If you mention the number of epochs to be lesser, then the value of W and B will not be perfectly optimized. Is that how many times you can say, for example, if I mention only 3 times, you must have reached this point, not this one, right? This is the best one. This may not be the best one, but you are limited by the number of epochs you mentioned. Fine. Okay. If you guys are okay with it, I will move on to the collab once again. Or if you have any specific doubt, you can ask. I know it is difficult to understand in one single go, but this is the core heart of any AI that you can find on Earth till today. This is how the model optimizes itself. Here, what are we trying to do? Instead of guessing the W and B values, right? We are trying to automate it so that the model itself can tune itself, self-learning, right? So if you understand this gradient descent, you have understood half of AI. I can promise you that. Yeah. Shall I move to the coding part? Yes or no? You just mention in the chat, please. Yes, one guy said yes. What about others? Is it like you are being overloaded? Let's move on to the coding part, sir. Anyway, we haven't understood the math. Is it like that? Let me keep both windows active, at least for some time. Just, yeah. Can you see the screen? Yes. Okay, now let's do one thing. Let's take the same data set and everything, right? Yeah, we have what? These are the data that we have, right? Cool. Let's keep it as it is. And then we have declared an arbitrary W and B. That is also fine. Some arbitrary W and P value. Generally, we keep it to be zero. We start with zero, but it's okay. Anything's okay. Okay. Then let me specify the parameters that we need. Let's make learning rate to be, say, how much? Let's make it 0.05. It is 2%, right? Epochs, let's keep it at maybe, I don't know. We can keep it at 100. Let's see. 100 iteration, or maybe let's make it even lesser, say 5 repetitions. Let us do at the beginning, and then we can see how it is affected, right? Then I will need what? N, let me take length of X, right? Length of data, basically, nothing else. So that is there. And then what? Now we need to put the entire prediction part inside a for loop. So I am doing it in a different way now. Y mean I am calculating at the beginning, then y underscore variance. I think I have already calculated that, right? Yeah, it is here. Let me take these two separately. Yeah, right. So now we need to start the for loop. For, let me do one thing. I will simply remove this part so that we can code it afresh, right? For I, any variable you can take, obviously, I in range of what? Number of epochs, that many times we need to repeat this, right? So epochs. What should we do? First of all, we need to try to calculate the MSE, right? To calculate MSE, what do we need? We need the predicted value, right? So for that, let me write y underscore predict is equal to what? Exactly. What is it? W into X. This is something that we already did yesterday. Minus, sorry, plus B, right? This gives me Y predicted value. Now let's calculate MSE. What is MSE? MSE is equal to NP dot mean, NP dot mean of what? Y minus Y underscore predicted, right? And we need to take a square of this square. This is what my MSE is, right? And then let me also calculate R square. We can calculate now, right? R square metric 1 minus what is this? MSE divided by variance, correct? We already have the variance here. This is what it is. This is the R square metric that we have. So let's do this print. Let's print both of these. F, what is this? MSC. Let's do something like this. Epoch number is what? I with what is the iteration that we are running through? I plus 1, right? Because I starts from 0. And then let's put some space. What is MSC? Let's print MSC is equal to MSC. Then let's put some space and then let's print R square. This is going to be R2. Okay. This is just for our understanding what is happening inside. Cool. Then we need to do what? We need to automate the process. We need to update W and B every time the loop is being repeated. So let me first calculate the DW. What is that? The we need to update the value of DW, right? The partial derivative we need to calculate. So for that, what was the equation? Minus of 2 divided by n, right? I hope you remember this, right? And then I can write something like this, np dot sum. What is it? Do you want me to share this the other screen as well? No, right? I hope you remember what is this? Summation of error multiplied by x, correct? So for that, what I'm doing, x star, right? Y minus y underscore predicted. What is this? This is error, plain error, not MSC. Please remember that, right? The summation I replaced with some function. Instead of xi, I have taken the entire data set. This is something to do with the Python. We can simply do this, right? Y minus y predicted, individual values get subtracted and then multiplied with x, right? Individual values get multiplied. This is star. Please remember, I'm not using at operator here, right? In the same way, if I write for db, it is going to be what? Minus 2 divided by n, right? Then multiplied with what? Np dot sum. Here, if you remember it, we did not have x here. It was simply error. What is error? Y minus y underscore predicted, right? This is db. Now we need to update current d value, sorry, current w value and p value. So for this, what should I do? I hope you remember w. Did I write plus in the beginning? No problem. We can write plus or minus. Depends on how you take dw and db. How come reconnect? Yeah, sorry. W minus. Let me write minus here. Doesn't matter exactly because minus of dw is plus. So either way it will reach. What is this? dw multiplied with learning rate. I hope you remember this from the whiteboard. So here also it is my b minus db multiplied with learning rate, right? That's it. This is what the essential part of gradient descent is. However, once we are done with the loop, please mind the indentation here, right? I'm coming back to the outer indentation. Here, let me print final figures, whatever we have found out. So print final values. W is equal to W. Then let me put some space. B is equal to B, right? Then let's predict whatever is happening. Y underscore predicted is equal to the same thing, W, X star W, anything is fine. Now if you want it in the proper thing, X plus B, right? Fine. The last part, let's keep it as it is. It is just plotting. However, we can do one thing last at the end. Let's calculate R square. Where is R square? This one. Let's print that also, right? This last part anyway is what? Plotting, right? So don't worry about it. I hope you already have this code, right? Shall we run this? Look at this. At the beginning, epoch number 1, MSC was 18, R square was minus 1.25. right? Epoch number 2, hold on, did I print? Okay, I didn't print this one, right? W and B, epoch number I plus 1, MSC and R square, I did print. Okay, let's do that. Let's do that also. Here, let me print W is equal to W, then B is equal to, yeah, look at this. Epoch number 1, W was 3, B was 2, MSC was 18, R square was minus 1.25, right? And then epoch number 2, W got reduced by 2.44, B got reduced by 1.84. MSC reduced to, from 18, it reduced to 5. Can you see this? R square, which was minus 1.25, it got improved to 0.36, right? And then W 2.145 in the epoch number 3, right? We are coming down the hill with respect to this. If you look at this, right? So B also got reduced again from 1.84 to 1.7536. MSC, look at the MSC, it is declining from 18, it has come down to 5. Now it has reached to 1.459, right? It is trying to reach the valley point where MSC becomes almost zero. This is what its objective is, right? And R square from R2 0.362, it increased to 0.81. It has improved, right? Look at epoch number 4. From 2.1456, now W has reduced to 1.99, B 1.70, right? And then MSC was this much, 0.46, and R2 was 0.94. Epoch number 5, again the same concept. So final value, right? 1.86. This is the if had we continued, this would have been the epoch number 6, right? So W 1.86, B 1.66, correct? This is the final value that we have printed here, over here. This is what it is, and final R squared is 0.9867. We can also print the MSC, final MSC, correct? See, 0.106. However, I hope, should I give some time for you to do the coding part? Yes, guys. Okay, please follow it up, write the code. I will try to remove the white spaces here so that the entire code fits in as much as possible. Okay, this much I think you have it from yesterday itself till here, right? So I will simply scroll up. I hope it is visible to everyone. Please type it out, get the output, and then we will do some modifications. Just let me know once you get the output. Guys, one thing I would like to tell you now is that if you are really confused about the math part that we covered today, you just ask for it. We can dedicate tomorrow's class specifically for that. We have some time, we can actually leverage that. Okay. And then on the, because this is very important, this you should really understand properly. How you found out the DW, why it matters, how we came about this formula, right? All these things we need to understand properly. Oh, correct. In the whiteboard, I wrote minus. Instead of minus, I wrote plus, I think. Actually, that does not help. If you have to use minus, why? Because when DW becomes negative, right, gets multiplied with this minus, yeah, whatever. When DW becomes negative, here it becomes negative into negative positive, so W value increases. Yeah. And when DW becomes positive, then here it becomes negative, it becomes W minus that value. So W value decreases. Correct. So if I have to that, let me correct it in the whiteboard. Okay, when I share the whiteboard at least. Okay. Were you able to get the output? Nice. We are already past 8:30. Generally, when I teach this part, the gradient descent algorithm, I usually take at least 4 hours, 4 to 5 hours. Right. Today I had to squeeze it to 1 hour so that you will get a taste of it. Obviously, it is a bootcamp course kind. So at least getting introduced to the concept is sufficient enough. So it's an introductory course, right? We can, if you are interested in the later course when I am doing the uh, complete math over AI, maybe you can join there and we can spend more time on the same thing. There we will have to look at everything like how partial derivatives work. Even we will have to take multivariate linear regression models where you will have to consider multiple features, not just X here. On the last day, we will be building a model which contains multiple variables. However, we will not deep dive into the maths of it because this itself is enough of a headache, right? Yes. Ananya, you want to say something? You can unmute and ask. Okay. Ananya is asking, could you take one more class for the maths part? I am still unclear. How many of you want this to happen? Just type in me too in the box so that I can get a clear count. Okay, one more. Okay. Deepak also wants it. Okay, Rajeshwari also wants it. Fine. Majority of you need clarifications, right? Fine. Then here is the task for today. I will, yeah, please raise your hands if you have completed the execution. Let's continue with today's process, right? Just 5 more minutes I need. And then we will wrap up here. I will again explain the math part tomorrow, right? We will not be doing any coding session tomorrow. Simply explore the mathematical aspect of it. I will do one thing. Let me explain the differentiation. What is differentiation? Some 5-10 minutes I'll do that tomorrow. And then we will look at the connection of that with the tangent, how it is related, right? And then what does the sign of the derivative tell you with respect to the tangent? That we will try to understand. Then we will move over to the gradient descent because that much of background is necessary. Actually, I usually plan to include calculus as part of the basics itself. But since we were doing some five days of basics on stats, linear algebra, and everything, I thought maybe I can include that in the later part. The class becomes boring, right? Yeah. Just raise your hands once you are done with the execution. Please. One person, two, only two, three. What about others? Four. Okay. I hope some 4 5 members did that. Shall I continue with the explanation? There is one important critical aspect that we need to observe. Okay. Let me get back to the collab, right? Now here, if you look at the output, right, we still have some error. See here, this is almost coinciding, but not this one, correct? And if you look at the MSC, it is not exactly 0. That is also there. R squared is not 100% or 1. That is also there, right? We could improve. So to do that, what I will do, I will simply increase the epochs to say 100. Okay. And if I do this, okay, no issues. Can you see this? Earlier we were at 5. There is 5 here. MSC was 0.18 and R2 was 0.97, right? After 100 epochs, the final value came out to be MSC got reduced to 0.021, right? And final R squared became 0.9973. That means what? I am able to explain 99.73% of the information, right? With these two W and B values, 1.90, 1.34. Of course, there are some errors. So if I increase, let me do one thing. This is really scary and we should not do that at all, right? So let me print it maybe after 25 epochs once, right? So if I percentage 25 is equal to 0. Oh, okay. I plus 1, right? Percentage 25 is equal to 0. Even for 0 also we can do I is equal to 0. Print it. Otherwise, I don't want to see this. Okay. Let me increase the epoch number to 1000. Even then it is going to be a difficult. Even 25 is too much. Let's make it 100. Essentially, what I'm doing, I'm just printing epoch number 1, first one, and then at epoch number 100, 200, 300, 400, I'm just reducing the printing. That's all. Okay. So after 1000 epochs, we arrived at what? Final MSE. Look at this. W is something like this. B MSC value, don't confused. It is not 1.0. It is 1.0 into e to the power minus 0.7, right? It is almost equal to 0, right? And then final R squared is 0.99999, almost equal to 1. Makes sense? So the thing is that the original value that would have given us full 100% R square and 0 MSC is actually W equal to 2 and B equal to 1, right? We tried it yesterday. We got 0 MSC and 1 R square. I hope you remember that part, right? So now after 1000 epochs, our algorithm is actually arriving at that particular value. See, so let's just increase it a little more, maybe 500 more. Yeah, look at the MSC. It reduced even more, 10 to the power minus 10. And here nines actually have increased, right? One thing that you should remember, I want to make 2 points here. One is as you increase the number of epochs, your algorithm will optimize itself even more. Okay, we are reaching the perfection more and more. That is one point. The second point, to reach the exact value is something that you will have to execute like for a huge number of times. Okay. And generally we don't do that. Once we arrive at certain points, there are of course different mechanisms, but if you follow this method for a simple linear regression algorithm, we generally uh, do an approximation, like we run it for, maybe if it is small, we run it for some 1500 or maybe 2000. Since the data set is small, it is okay. What about a larger data set? Say we had some x entries, number of rows was here, how much was it? 3 plus sorry 5, right? Only 5 values we had. Instead of 5, what if we had 1 million entries, even 2000 entries? Difficult, right? So in such situations, we generally optimize it. That's it. We simply do the approximations. We round it off or do something like that. Okay, cool. If I change this one, this is simply a odd number trend. It is following. That is why we are able to reach it. Let me do one thing. Let's simply make it some 3, 5. Instead of 7, let's make it 6. Okay, then run this. See, so with this kind of problem, you are never going to get 1 R squared, because even after 1500 epochs, if you see, it is trying to match up with the remaining ones, but this one value is actually creating the error. Because of this one, it is trying to move closer towards this point also, just to minimize the error. That is why we got errors over these 4 points as well. Okay, as the number of samples increase, as the variance increases, you will not be able to reach 1 R squared value. Never. Okay. So the good rule of thumb is something like something above 0.80 is good enough. Okay. That is there. So let's wind this up, right? I will just show it to you once again so that you will be able to follow it up. If you haven't done the coding part yet, just watch the video, pause it here, do the coding, and then complete it. Change different epoch values. You can also experiment with W equal to 0 and B equal to 0, right? How these things change is also I can do, right? See, we actually arrived at the same thing. 2. Now here, if you look at this, B value is roughly 0.8. Fine. You can experiment with your own values. Try this out. Fine. Just to correct it as part of the video, I will share the whiteboard once again, where I have corrected that part. Which one? The formula. You can see this, right? Can you? Hold on, just a second. To the meeting, share it. Just to document the change. That's all. Yeah. Yes. This very small change. What is it? This part. We had made a mistake here. I had made a mistake here. I had written W plus DW and B plus DB. Okay, if you do that, it becomes unbounded. It will not converge into the valley point. It will not come down like this. Instead, it will go away like this. Okay, just keep that in mind and make this change noted in your mind. Cool. Shall we end the session? And obviously, you have doubts. So let's do that. Tomorrow I will address the math part once again. Okay. So day after tomorrow, the last one, that is more like you watching a cinema. I will build a linear regression model on a real data set where there are multiple features. Okay. We will try to predict something. Fine. I'll just show you how the process is, like how do you clean the data, uh, how do you fix the null values in a real data set, then how do you encode it into the same logic. I'll take the same logic and do it. Fine. And if time permits, we can also just look at how libraries are made use of. Cool. Yeah. Thank you guys. If you have any specific questions, you just ask in the WhatsApp group.